Welcome to Cuttin It Close, a channel where we talk woodworking technology, a little bit of business, and make some cool projects. And in today's video, we're going to go over some lessons that I've learned after thousands of hours of machining on a CNC that nobody really talks about and could save you a lot of time and money. And so how we're going to go about doing this video is I'm going to go up to my office and show you my process of calculating chip load that I've shown in a previous video, and then I'm going to point out where these problems arise. And the three major problems that we're going to look at is centrifugal load on a bit, the torque on a spindle, and the acceleration and deceleration of bits. So, with that being said, let's go look at problem number one. Alright guys, so now we're at my chip load charts that I showed you on a previous video. And I did do a metric version of this for all of my metric out there. And I would like to know if y'all wanted me to make a website showing you all of this and so that you can access. So please let me know if you would like to see this, if it'd be worthwhile for me to go ahead and make it if I have enough demand for a website showing you these chip load charts. Now the stuff I'm about to explain, if you don't understand what chip load is, please go watch my other video over chip load and then come back to this, because this could get confusing if you don't understand, okay? This one's probably one of the harder ones to grasp, but it's the most important, okay? So let's say you have a 1/4 inch bit and you're cutting into hardwood once again, let's just make it simple, or a 6mm bit cut into hardwood, okay? So we need a chip load of 0.01 to be right in the middle of it, okay? So let's get a chip load of 0.01 right there, okay? So that's 300 inches a minute at 15,000 RPMs, okay? Well, let's say you're cutting a 4-inch square, so just a small square, right? Your spindle may never get to 300 inches a minute. So what you're going to have to do is lower down your feed rate to, let's say, 200 inches a minute, and then adjust this accordingly, okay? And so now you have the same exact chip load, once again, as earlier, but now your feed rate is much lower and your RPMs are much lower. So if you learned anything about the torque one, about the torque lesson I just taught you, maybe you can do this, maybe you can't, depending on the bits and all that stuff you have. But this may be a better option than this when you're cutting a small square, okay? When you're cutting, let's say, a square this size. The reason being is because that bit has to accelerate and decelerate and get to 300 inches a minute in order for this chip load to happen. I know this seems a little confusing now, so let's go down to the shop so I can explain why this option is sometimes better, even though it's the same chip load, is sometimes better than this option, which is the same chip load but a little bit faster feed rate. So let's go down to the shop so I can explain to you this problem. So how this acceleration and deceleration of corners and turns happens in a CNC is that, imagine you have a box that you're cutting out and it's, maybe this long and it's a perfect square, okay? And if you're running something at 400 inches a minute or 200 inches a minute, let's say, your CNC may not, your servo motors and everything may not be able to get up to speed to even ever reach that 200 inches a minute or that 400 inches a minute, whatever it is. So based on the power of your servo motors is where this problem arises. Now, let's think of vehicles, okay? Let's think of you're driving your car and you want to go 70 miles an hour, but you only have a block to go, right? Just a city block. So you gas it, right? And you start accelerating as fast as you possibly can. Well, then you have a stop sign at the end of that city block. So you have to put on your brakes and then turn and then go around the next corner. And then you try to get to 70 miles an hour again, but you never can reach 70 miles an hour or 70 kilometers an hour, depending on where you're at in the world, right? Because you have to stop for the next corner. So now apply that to a CNC, where that bit wants to reach that 70 kilometers an hour, 70 miles an hour, but it has only 4 inches to reach that. So really, it only reaches, if you want to go 100 inches a minute, it may only reach 50 inches a minute. Or apply that to vehicles where the car maybe wants to go 70 kilometers an hour and it only reaches 40 kilometers an hour. So what you have to do as a CNC operator is kind of, and this is not, once again, it's not exact math, but you have to idle down your vehicle or idle down your RPMs of your spindle to adjust for that, okay? Now I'm gonna give another example on a piece of wood real quick, and then I'm gonna come back and kind of talk about how I adjusted for that personally. So let me take out this CNC bit real quick. Okay, so think of this as a cut path you're cutting on your CNC, right? And this red dot is the bit and or car, and this is like a city, like a weird city street, right? And when I said kilometers and miles per hour, I know they're not the same, but you know, in reference, 70 miles an hour or whatever, 145 kilometers an hour, whatever it is, just know that it's in proportion, okay? So if your vehicle's starting right here, or your bit, it has to accelerate. So maybe right here it's going 20, it's going 30, it's going 40, then it has to go down to 30, 20, and 10 once again. So accelerates, decelerates, takes a corner, accelerates, and maybe it only gets to 20 right here, then it has to decelerate, back, hit that stop sign, take another turn, and then it goes and it slows down again, and it takes, so this long straightaway right here, maybe that's the only time in these 2 points right here that it actually gets to that feed rate that you're wanting it to get to. So all over here, it's actually burning up this bit, this is a burnt bit. It's actually burning up this bit a little bit faster than it should be, because the only spot it's ever reaching, that feed rate is right here. Now if you're cutting long paths, I mean just really long paths, that's not a big deal. But whenever you're cutting these smaller tool paths like this, you start running into that problem. Now a way that I have in the past came across and fixed this problem is I've eliminated corners. So if you think of a city street and you think of whenever they put a corner in, like around this stuff, around these major corners, and if your product allows you to do this. So you're cutting and your bit now is going, let's say it's at 10, 20, 30, well it doesn't have to slow back down to 0 to make a stop to turn. Now it's cutting corners like that. And the only time it slows down is a corner like this. And so you're running that bit and then it slows down a little bit, makes a corner, and then speeds up faster, right? And so then it can reach those maximum speeds a lot better. So if you're machining a product and you're sanding the corners down anyways, cut those corners off with a CNC and have rounded edges, because it allows that bit to gain its maximum speed a lot faster, and it doesn't have all these starts and stops. Once again, think about your vehicle, and when you're driving on a highway or an interstate or a major road, and it has a stop sign versus a turn, you have a lot more efficient flow of traffic whenever there's a turn instead of a stop sign and a stop and go. I hope this kind of helps. Now let's go back to how else I eliminated problems with this. So how we at my company adjusted for that problem, we ran a tool path that we wanted to run, right? And then we timed it. Okay, and then let's say we're running it at 200 inches a minute and it took 10 minutes to cut this thing out, right? Well, we timed it and we lowered it down to 150 inches a minute and lowered the RPMs correctly, and the time didn't decrease any. It still took roughly 10 minutes to cut that piece out. Well, what that means is it was never getting up to speed in the first place. And since my company machines a lot of small parts, we have this problem a lot, specifically on pocketing, right? When you think of pocketing something, you're going, little short, and then it gets longer, and then it gets wider, right? And then it finally pockets out the whole thing. Or if you're pocketing this way, the little stops whenever it goes and does a raster, I believe it is. So with that being said, one thing you can do to at least get close, once again, you have to do a lot of math to get it exactly 100% right, is time it, right? If you're running something at 200 inches a minute, or 400 centimeters a minute, whatever you're running it at, time it and see how long it takes, and then you don't even have to cut anything. Just let your CNC run, without anything in it, right? And then time it again, slow it down 50 inches a minute, or 75 centimeters a minute, and run it again and see if that time changes. If there is, let's say in proportion, you slow down your feed rate by 50% and your time slows down by 50%, then you're good. But if you slow down your feed rate by 50% and your time only drops 2%, well then you know that spindle, that CNC, them servo motors are never getting up to speed in the first place. And in the CNC world, we call that like servo motor quickness, right? How quickly can it accelerate and decelerate on those corners? So let's go over the first problem, centrifugal load, okay? Now, let's say you have a bit and you say, and this is only going to apply to larger CNCs, but this is still good to know information to you. So let's say you have, your chip load needs to be 0.018 on a bit you're running, and it's a very wide bit. Let's say it's a 2-inch fly cutter, okay? So you're servicing some wood or servicing a spoil board or something, and it's a 2-inch fly cutter bit. Okay, well, so your feed rate's 425 inches per minute, or almost 11,000 millimeters a minute, 12,000 RPMs, etc. Okay, that's the correct chip load. Well, let's say your CNC can go 800 inches per minute. And so you go, hey, well, why don't I just speed up this to my maximum RPMs it can go, and then just speed up my feed rate, and then let's see if I can get that 0.18 that I need, right? Okay. Well, you can't just speed up your RPMs and your feed rate. Even though it's the same chip load, it's too much RPMs for that bit to bear, okay? So let me show, and this is how the first problem arises, this simple little mistake right here. So let's go down to the shop, and I'm going to show you why this right here is a problem versus having this. Okay, this is correct. This is a problem. Okay, same chip load, but this is a problem. So let's go down to the shop and let me show you why. So this centrifugal load problem that I talked about, I've never personally experienced. I've just heard from different machinists and people that make bits that this problem can occur. So this is a very simple problem. It should be pretty simple, relatively simple to explain. And so this is the problem that happens whenever you take a really long bit or a really wide bit and turn up the RPMs way too much, right? So if you know how a centrifuge works, right, it spins really fast and everything goes to the outside. Well, there's a certain load point on different bits that it cannot take the, I don't know what the physics word is, but cannot take the force exerted to the outside, right? So we have this fly cutter right here. Now this is a decently big fly cutter, so you may not have one this big, but kind of think in terms of your machine size and your fly cutter, right? So this is a pretty decent size fly cut bit that I have, and what this does is I won't be able to spin this at 24,000 RPMs. This is what's going to happen is these carbide tips and all this spinning and stuff is going to cause this minute vibration. But if it's off just a little bit of a percent, right? If it's not just perfectly at a perfectly straight down, what's going to happen is this little bit of vibration, and then you got a lot of vibrations going to start happening. And this bit is either going to start tearing apart or it's going to tear up your spindle itself, okay? Now, let's say you have a very long bit. Now, a bit is long relatively to the size of CNC you have, right? So to this bigger CNC, a long bit could be 4 inches. But to your hobbyist CNC, a long bit could be 3 inches, right? Because you have a smaller CNC. Well, what happens if you have a very long bit, once again, if it's not perfectly straight down and it has a little bit of a lean to it, right? Just a little bit of a lean. Let's say it's like this. Well, when it starts spinning and you have that higher RPM, it's going to start wanting to rattle and shake, and then one thing you're going to have is not a clean cut, and the second thing, when it's rattling and shaking, it starts bouncing around and popping in that wood, and then your bit's going to break. So that's the other reason. Now, if your bit is in a perfect world, right, the bit's going to be perfectly straight down, and you're going to have no problems, right? But the world's not perfect, and you're going to be cutting at the same time. So there's going to be a little bit of bend and snap, right? And and so your bit's going to be popping in that wood, and then that's when centrifugal load comes into play. So instead of running a bit maybe like this at 24,000 RPMs, I have to run it at around 10,000 RPMs so it doesn't shake and rattle. Now, it's not a perfect science to it, like what's the perfect RPMs to run it at, but just know on longer bits and really wide bits, you're not going to be able to run at a super high RPM because of that centrifugal load problem. Perfect. Let's go look at the next problem. All right, guys, so now we're going to look at torque. So let's say that you want to run a 3/8 inch bit into hardwood or a 10 millimeter bit into hardwood, which is the same, okay? So you need to have a chip load between 0.015 and 0.018. So let's just go 0.016 is what we're going to want to do. So let's say you're going to run at 18,000 RPMs and you're going to need 0.018, so you're going to have to run it at 750 inches a minute. Let's see, 600, somewhere around there, okay? So that fits the correct chip load for cutting a 3/8 inch bit into hardwood, right? 0.017 matches that, okay? Well, now let's say you have a smaller CNC and you can only go 300 inches a minute, okay? Or, 7,600 millimeters a minute. So say you have a smaller CNC, you can only go 300 inches a minute. And you still want to use that 3/8 inch bit. So you just go, well, I'm going to idle down my RPMs to still have the same chip load, right? Same chip load as before, but you can't reach 600 inches a minute because of your CNC, and so you just idle down the RPMs to 9,000 RPMs. Well, two things happen with that. One is that your CNC, your spindle may not be able to go down to 9,000 RPMs, and secondly, you cannot do this right here. You cannot run that at 9,000 RPMs because of the torque it's going to put on your machine. And so let's go down there and show you why this right here is a problem. Even though same chip load, right? So you think, okay, I found the chip load, I'm good. Well, once again, problem lies in, even though it's the same chip load, those RPMs are not going to work. So let's go down and I'm going to show you why that's a problem. So this problem isn't really just a torque problem. It's kind of an overall power of the machine and your limits of your spindle. So my spindle can't go down to 6,000 RPMs. I think its minimum is 8,000 RPMs, right? But even with that, I can't run a 3/8 inch bit at 8,000 RPMs in order to get the right feed rate. I learned this in all practicality when I was using a 3/8 inch bit to run in some plywood, right? And what happened after about a foot, my spindle started making kind of a funny sound and started bogging down, and then my bit broke. And I didn't understand why, because it was the correct chip load. Well, there's a couple factors that come into play with that. One of the factors is you got to take in consideration is wear and tear on your machine. So if you're always pushing a bit with that amount of force, it's going to hurt your servo motors over time. And two, it is going to bog down your machine. And why this machine bogs down because of that force is that this has to have enough horsepower to produce enough torque in the bit where the bit has that shear force where it's cutting. Well, what happens is when you're running it that slow, there's not enough torque this thing can produce. I don't even know if it's exactly torque, but to me it's torque. It's enough force for that bit to spin and have that shearing action and the shear force to cut the material. So when you go down, let's say you're running a 1/2 inch bit at 8,000 RPMs in order to go down to a certain feed rate, and you're putting it on this spindle does not have enough horsepower in order to create that amount of shear force at that RPM. Now there's not just a exactly perfect science to this. Once again, you're going to have to figure it out for yourself and kind of see what your spindle can handle. But just know, once it starts bogging down, it's because that RPM of that spindle does not produce enough torque on that bit for the shear force to be correct. And when that shear force isn't correct, it starts to bog down, your spindle's going to heat up, and it's not good for your spindle or your router, whatever you're using. And then after that happens, your bit's going to break. Now, for those of you that have routers instead of spindles, you have a lot less variableness on your RPMs, right? Because it may only be 1 RPM or maybe, 16,000, 18,000, 24,000. So you're going to have to play with it a little bit, and really you got to learn the sounds of your machine and what type of material there is, right? So just know there's a lot of variables when it comes to that, but just don't think you can slow it down to 10,000 RPMs in order to adjust for this certain feed rate, because you have to take into consideration the amount of torque and everything you're applying on your overall machine, on your servo motors and stepper motors, and also your spindle itself. Once again, not an exact science, but I'm just trying to give you information that I have learned that cost me money over time. All right, guys, I really hope this helped y'all. I hope you came out better than when you started this video. And these little drawings like this, though they may be very simple, it's just understanding the fundamentals of it. If you can understand the fundamentals of these little problems and tweaks and adjustments, you start putting yourself in that upper level of CNC machinist, and your products really start shining through, and you use less bits and you save more money and save more time. So that was kind of the purpose of this video. I just want y'all to come out of this video better than what y'all started, and I hope I did that. So with that being said, please let me know what you like to watch in the comment sections below. And remember, if you ain't cutting it close, you ain't cutting it right.